In this video, we are going to continue doing problems that we started in the last video. So if you recall, in the previous video, I wanted to compute the maximal ideals of certain rings. So I'll show you the problem that we were doing, and we did half of it. So the question was to compute maximal ideals or find the maximal ideals of these four rings, Z and Rx mod x squared. We did the first two, so let's do now the remaining two here. And in this problem, I will also recall some facts that we have learned before. So the problem is to compute the following. So find the maximal ideals of Z and Rx mod x squared, Rx mod x squared plus 1 and Cx mod x squared plus 1. So we have already done this, and for the second problem, the crucial idea was that the correspondence theorem, which says that if you have a ring R, ideal I in it, and the ring R mod I, the quotient ring, there is a bijective correspondence between ideals of R that contain I and the ideals of R mod I. And this bijection, in fact, carries over to prime ideals as well as to maximal ideals. So using that, we used that to find out the maximal ideals of Rx mod x squared. These are maximal ideals in Rx that contain x squared, and by a simple calculation, we saw that there is only one such, namely the ideal generated by x itself. So in order to continue this problem, let me use the following fact, which I did when I first introduced polynomial rings. So let's say K is a field, and let's say R is the polynomial ring in one variable over K. So R is Kx. So then what we have is that recall two things. Every ideal of R is principal. Okay, remember, principal means if I is an ideal, so this is what I mean, if I is an ideal, then I is in fact generated by a single polynomial for some f in Kx, okay, which is of course R. So remember this notation here, f within brackets means the ideal generated by f. This consists of all multiples of f, and that's when we call it a principal ideal. And recall the proof of this I did using Euclidean division algorithm. The idea is to pick the polynomial in I whose degree is smallest, positive degree polynomial whose degree is smallest, and then we use Euclidean division to show that every other polynomial that is in I is a multiple of f. Now second fact I will write, which maybe I did not mention this explicitly before, but it's an easy exercise. An ideal I in Kx, which is again R, this is a statement which is very special to polynomial rings over a field in one variable. So an ideal is maximal if and only if f is irreducible. Okay, so this is not a difficult exercise, so I will just give you a quick hint to do this. So one is something we have done before. Hint for two, the problem is not to do this exercise, I will rather do the previous exercise that I wrote. So I would like you to prove 2 for yourself, but I will give you a hint. Okay, so suppose f is not irreducible. Remember, an irreducible polynomial is one which cannot be factored into two polynomials g and h, where g and h are actually not equal to f or not equal to 1. So f is not irreducible means f can be written as a product of two polynomials in the polynomial ring, and the point of course is that g is not f, h is not f. You can always factor a polynomial as 1 times f. If it is not irreducible, it can be factored in a more interesting fashion, non-trivial fashion. So then the ideal Okay, by the way, I should not, I didn't write this carefully. An ideal I, so I will just, I will not mention I here. The problem, the exercise is to show that an ideal generated by a single polynomial is maximal if and only if f is irreducible. So the ideal f is contained then, right? So what I mean is this, because f is GH. Remember, the ideal generated by G is the set of all multiples of G. F is one such multiple because G times H is F. So this belongs to this and it's not equal, right? It's an easy exercise to show that F is not equal to G because G is a polynomial of strictly smaller degree. Otherwise, G will be equal to F. Here we need that G and H are not constant polynomials. That's what it means for F to be not irreducible. So G and H are not constant polynomials. So degree of G is strictly less than degree of F. So this cannot be equal to this, right? Because G is not in the ideal generated by F. Because if G was a multiple of F, degree of G will be at least the degree of F. But degree of G is less than degree of F. At the same time, the ideal generated by G cannot be all of Kx because degree of G is positive. It's not a constant polynomial. So no ideal generated by a non-constant polynomial can be the unit ideal. So this concludes the statement that F is not maximal. So I have proved one direction for you. If F is not irreducible, it cannot be maximal. The other direction is if F is actually irreducible, show that the ideal generated by F is maximal. I will not do this for you, but the idea is, suppose the ideal is not maximal, then ideal generated by F is contained in a proper ideal which is bigger than that. But because of fact 1, every ideal is principal. So let's say the bigger ideal is generated by G, then you argue that G must divide F, violating the irreducibility of F. So the other direction is left for you as an exercise. Okay, so this is an easy exercise actually. So I strongly urge you to do this carefully. So this is a fact that I am going to use. Now coming back to the problem. So let's first consider the quotient ring Rx mod x squared plus 1. What are the maximal ideals of this? Let's call this ring R. What are the maximal ideals of R? This is, remember, the third part of the previous problem. So what are the maximal ideals of this? As we agreed by the correspondence theorem, max ideals of R come from max ideals, the ring R. Now max ideals of R come from the polynomial ring Rx that contain the ideal generated by x squared plus 1. But now recall, this is something I have done at least in two different ways in previous videos. The ideal generated by x squared plus 1 is already maximal in the polynomial ring in one variable over the real numbers. So this I have checked in fact for you. So that means there is only one ideal that contains x squared plus 1 in Rx, namely the ideal itself. In fact, there are two ideals that contain x squared plus 1. One is x squared plus 1, the other is Rx, the unit ideal. But there is only exactly one ideal which is maximal and which contains x squared plus 1. So there is exactly one maximal ideal in Rx that contains x squared plus 1, which I used to conclude that there is only one maximal ideal in the quotient ring. Right, so I have skipped a step here. The maximal ideals of Rx mod x squared plus 1 are in bijective correspondence with maximal ideals of Rx that contain x squared plus 1. But there is only one maximal ideal in Rx that contains x squared plus 1. So there is exactly one maximal ideal in Rx mod x squared plus 1. And what is that? And that ideal is the zero ideal, because remember, if an ideal, maximal ideal of Rx contains x squared plus 1, its image under the canonical map from Rx to Rx mod x squared plus 1 is the maximal ideal of Rx mod x squared plus 1. If x squared plus 1 is that maximal ideal, its image is the zero ideal, because the ideal x squared plus 1 gets killed in the quotient ring Rx mod x squared plus 1. So Rx mod x squared plus 1 has a unique maximal ideal, and that is a zero ideal. But remember, there is a special name for rings that have this property that the zero ideal is a maximal ideal, which is that Rx mod x squared plus 1 is a field, because 0 is a maximal ideal in this. That means every non-zero element is a unit. So this is the field. But in fact, we already knew this. Why? Why did we know this? Because Rx mod x squared plus 1, when I showed that x squared plus 1 was a maximal ideal in Rx, in fact I showed that Rx mod x squared plus 1 is isomorphic to C as rings or as fields. So there is only zero ideal which is maximal. So this is easy. Maximal ideals of Rx mod x squared plus 1 are, there is only one, and that's a zero ideal. Now let's look at Cx mod x squared plus 1. So just a final comment about the previous problem, Rx mod x squared plus 1. What we have concluded is that the ideal generated by x squared plus 1 in Rx is maximal. Remember, this is a fact that I said here. So x squared plus 1, the ideal is maximal. And this is also verified by the fact that I wrote, which is that an ideal is maximal if and only if its generator is irreducible. And we do know that x squared plus 1 is an irreducible polynomial in the polynomial ring Rx, because a degree 2 polynomial is irreducible if and only if it has no roots, and the polynomial x squared plus 1 has no roots in the field of real numbers. So its ideal generated by x squared plus 1 is in fact irreducible. So the ideal generated by the irreducible polynomial x squared plus 1 is in fact maximal. Now this is no longer the case here. So to find maximal ideals of the, now let's come back to Cx mod x squared plus 1. In order to find the maximal ideals of this ring, we are going to find max ideals Cx that contain, okay, so now we are interested in finding ideals, maximal ideals of Cx that contain the polynomial x squared plus 1. So containing the polynomial x squared plus 1 is equivalent to containing the ideal generated by the polynomial x squared plus 1. Now immediately, unlike in the previous case, we see that unlike in the previous problem when we were dealing with real numbers, this is not maximal, I claim. This is not maximal in Cx. And the reason is, every ideal in Cx, remember by our general fact, is principal. And it is irreducible if and only if the generator is actually an irreducible, it is a principal ideal generated by a polynomial f is prime or maximal rather if and only if f is irreducible. Now the point is x squared plus 1 is not irreducible in Cx. This is the difference between real numbers and complex numbers. Why is it not different? Why is it not irreducible? That is because now it can factor. as x plus I times x minus I, where of course I is a square root of minus 1 as always. Remember, I is not available in the real numbers, so you can't factor x square plus 1 in Rx. However, you can factor it in complex numbers. So Cx, in Cx, x square plus 1 has 2 factors, so it's not irreducible. So immediately, if you see from the previous the exercise that I left for you, you see that the argument in that exercise tells you that the ideal generated by x squared plus 1 is contained in x plus I and also x minus I. So there it is, you see that it's not maximal because it is contained in a bigger ideal, which is a proper ideal. X plus I is strictly bigger than x squared plus 1, the ideals, and x plus I is in fact not equal to the full ring Cx because lots of polynomials are not there. For example, the element 1 is not there. So this confirms that x squared plus 1 is not irreducible. So there are at least 2 maximal ideals in Cx, and also I should mention that though x squared plus 1 is not maximal, this is maximal. This is also maximal. So this I will leave for you as an exercise. Again, using the fact that I told you, which was in fact an exercise, is that a principal ideal generated by a polynomial f is maximal if and only if that polynomial is irreducible. Here the ideal is generated by x plus I, and x plus I is in fact an irreducible polynomial. You can clearly check that. It's a degree 1 polynomial. You cannot possibly factor it as a product of 2 positive degree polynomials. So this is irreducible, x minus I is irreducible, so the ideal generated by them are maximal. So we have at least, at this point we can only say this, at least 2 maximal ideals in Cx that contain x squared plus 1. Okay, but now that implies by the correspondence theorem Cx mod x squared plus 1 contains at least 2 maximal ideals. Now the question is, are there any others? Are there more? So you have at least 2 maximal ideals, unlike the ring Rx mod x squared plus 1, which has a unique maximal ideal. The ring Cx mod x squared plus 1 has at least 2 maximal ideals. Are there more? So if there are more, you will have a maximal ideal generated by a single polynomial fx, which is irreducible in Cx, and the ideal generated by fx contains the ideal generated by x squared plus 1. So now I will leave this as an exercise to show that there are no more. And the reason is, if x squared plus 1 is contained in the ideal generated by fx and it's not equal to fx, and let's say fx is also not equal to the full ring, it's not the unit ideal. If these 2 facts hold, that means that degree of f is exactly equal to 1, because if it's 2, it must be equal to x squared plus 1. If it is 0, it must equal the unit ideal. So it cannot be more than 2. It cannot be more than 2, and it cannot be 0. So it has to be 1. But if it is 1, then fx must be of the form x minus a belonging to C. But once that happens, you can assume that f is monic, because you can always multiply by the inverse of the leading coefficient and assume that fx is monic. So fx is x minus a, but then if x squared plus 1 is contained in x minus a, this implies that a squared plus 1 is 0. So this little fact is an exercise for you. Because x squared plus 1 belongs to x minus a, that means x squared plus 1 is x minus a times something, Now you plug in plug in a in both sides, you will get that a squared plus 1 is equal to 0. But that means a is equal to I or a is equal to minus I. So this is the only possibilities. Remember that we already considered x plus I and x minus I. This we already considered. So in fact there are exactly two maximal ideals in Cx mod x squared plus 1. Hence there are exactly two maximal ideals in Cx mod x squared plus 1. And I will leave this, they are x plus I and x minus I. And now I will leave a final exercise regarding this problem for you. We know that because x plus I is a maximal ideal, Cx mod x plus I is isomorphic to a field. What field is that? In fact, that is just isomorphic to C. And similarly, Cx mod x minus I is also isomorphic to C. This you can use first isomorphism theorem. Define a function from Cx to C by evaluating a polynomial at I. So fx goes to f of I. Show that it's a surjective ring homomorphism with kernel being x plus I or x minus I. So you have to consider two different homomorphisms. So this is an exercise for you. Okay. So this finishes the problem where we were computing maximal ideals of various rings. Okay. So now I will do one more problem here. I lost track of the number, but it's a different problem similar to the previous problem, which is that show that z mod 2z x divided by or quotient x cubed plus x plus 1 is a field, and second part is to show that z mod 3z x by the same polynomial is not a field. Okay, so the question is to show that I consider two polynomial rings, 1 over z mod 2z, that's, remember, a ring which is in fact a field. Z mod 2z and z mod 3z are fields containing, this has 2 elements, this has 3 elements. They are fields containing 2 and 3 elements respectively. So I take a polynomial ring over those fields, consider the ideal generated by x cube plus x plus 1 and look at the quotient ring. In one case it happens to be a field, in the other case it doesn't form a field. So why is that? By the fact that I wrote at the beginning of this video, x cubed plus x plus 1, first consider the field case, z mod 2z x. So x cube plus x plus 1 in z mod 2z bracket x is maximal. So I will write, so this is not by the fact, so let's leave this aside. So what I will do is z mod 2z mod x cubed plus x plus 1 is a field if and only. So this is confusing. I am not organizing this properly, but hopefully it's not confusing. Z mod 2zx mod x cube plus x plus 1 is a field. This is what, remember, we are trying to show. This is what we want to show. It is equivalent to x cube plus x plus 1 being a maximal ideal in Z mod 2zx. This is an equivalent definition of a maximal ideal. An ideal I in a ring R is maximal if and only if R mod I is a field. So this is a field if and only if this is a maximal ideal in this. Now by the fact, this implication is by the fact this is a maximal ideal if and only if x cube plus x plus 1 is irreducible in Z mod 2zx. Remember, an ideal generated by a polynomial fx in Kx, where K is a field, that's important, is maximal if and only if that generator is irreducible. Because it's a degree 3 polynomial, a degree 3 polynomial is irreducible if and only if x cubed plus x plus 1 has no roots. This may be, I mentioned before, in Z mod 2Z. Remember, you have a polynomial f which is degree 3. How can it fail to be irreducible? Remember, a degree 3 polynomial, in order to be not irreducible, it must factor as two polynomials, product of two polynomials g and h. But because degree is 3 of f, degree of f is 3, the sum of degree of g plus degree of h is 3. And they are both supposed to be strictly less than 3. That means they have, one of them has to be degree 1, the other has to be degree 2. Right? This is the only possible breakup of the degrees. Because if either of them is degree 3, then it cannot be a valid factorization. For it to be a valid factorization, both of them have to have degree strictly smaller than degree of f, which is 3. So you have two numbers which are strictly less than 3, which add up to 3 positive numbers, of course. They are both 1 and 2. But a degree 1 polynomial is really of the form, if g is degree 1, then g must be of the form x minus a. But if x minus a divides f, f of a is 0. That means f has a root, a is a root of f. So if the polynomial in question has no roots, it cannot factor. This is only true for degree 3 or 2. So here at degree 3, so it has no roots if and only if it is irreducible. But whether it has a root or not is easy to check, because Z mod till Z, remember, has only 2 elements. Okay, let's plug in both of them and see if they are possibly roots. So x cubed plus x plus 1, let's call it fx for simplicity. And what is f of 0 bar? This is 0 bar cubed, 0 bar plus 1 bar, which is 1 bar, not 0 bar. So f of 1 bar is 1 bar cubed plus 1 bar plus 1 bar, which is 3 times 1 bar, which is actually equal to 1 bar, which is not 0. So we conclude that neither of the two elements in Z mod 2Z is a root of fx. So f has no root in Z mod 2Z. That means this statement is true. That means this statement is true. That means this statement is true. That means this statement is true, which is exactly the first problem. Now, if we consider the other field, Z mod 3Z, we have to essentially consider the same set of equivalences. Z mod 3Z x mod x cube plus x plus 1, remember the same polynomial, is a field if and only if this is maximal, if and only if this is irreducible, if and only if these are no roots. But f does have a root. In Z mod 3Z. For example, if you take f of 1 bar, it will now happen to be 1 bar cubed plus 1 bar plus 1 bar, which is 3 times 1 bar. But 3 times 1 bar is 0 bar in Z mod 3Z. So f has a root in Z mod 3Z. So the ideal generated by f in Z mod 3Z x is not maximal. Hence, Z mod 3Z mod x cube plus 1, x cube plus x plus 1 is not a field. So we have solved both the problems. So you can see that if you change the coefficients, the field where the coefficients of polynomials come from, ideals behave very differently. In one it is maximal, in the other it is not maximal. Okay, so let me end this video now with a final problem. This is useful. This is a simple problem also, but I might use these facts later. So this is also about prime and maximal ideals. So let me state this. I'll quickly write the problem and tell you how to solve it. Maybe leave the details for you. Let's say phi from R to R prime is a ring homomorphism. Okay, this is a ring homomorphism. So I will write down a series of statements, then show that If P is prime in R prime, is a prime ideal, implies phi inverse P is a prime ideal in R. This is the first problem. You take a prime ideal, take its inverse image, it's a prime ideal. 2. The above statement does not hold for maximal ideals. In this problem, I am only considering inverse images of primes or inverse images of maximal ideals, and I am claiming that if you take the inverse image of a prime ideal, it happens to be prime. Inverse image of a maximal ideal cannot be, is in general not maximal. It may be maximal, but in general it need not be. So let's do this. First part, we already know that phi inverse P is an ideal. See, in order to prove that phi inverse P is a prime ideal, we first need to show that it's an ideal. But that we have shown before. Inverse image of an ideal under a ring homomorphism is an ideal. This is easy to check. Remember, things are different when you are talking about the image of an ideal. In general, image of an ideal is not an ideal. You need the homomorphism to be surjective. But there is no such problem for inverse image under a ring homomorphism. Inverse image of an ideal is always an ideal. Now all we need to do is, so far we have only used that P is an ideal, phi inverse P is an ideal. Now we need to use the fact that P is prime to show that phi inverse P is also prime. So to show that phi inverse P is prime, what do we need to show? Let A comma B be elements of R, and suppose that AB is in phi inverse P. Okay, so as I said, this is a fairly straightforward verification. So what is a prime ideal? It's an ideal such that if a product belongs to the ideal, one of the elements must belong to the ideal. So let's take two ring elements whose product is in phi inverse P. Then phi of AB is in P by definition. AB is in the inverse image means phi of AB is in P. That means phi of A times phi of B is in P, because phi is a ring homomorphism. Phi of AB is equal to phi of A times phi of B. Now because P is prime, phi of A is in P or phi of B is in P. Because P is prime, that's hypothesis. But that means A is in phi inverse P or B is in phi inverse P. As required, right? I started with the product that's in phi inverse P, and I have concluded that one of them must be in phi inverse P. So this is easy, straightforward, just the definition. Now why do I say that the second statement does not hold, the same statement does not hold for maximal ideals? So consider phi from Z to Q. Phi from Z to Q. So this is just the inclusion map. Phi of N to be N for, or let's say phi of R equal to phi of R equal to R for, I should really write N, sorry, is N for all N in Z. So this is just Z sitting inside Q. Take an integer and send it to itself. This is a ring homomorphism, of course. Z and Q are rings, and this is certainly a ring homomorphism. Now what is the maximal ideal of Q? Let I be the zero ideal in Q. Then I is of course maximal ideal. Of course it is maximal. And what is phi inverse I? Because phi is an injective map, phi inverse 0 is just 0 again. And of course it's an ideal, as I told you, inverse image of ideals is ideal, is an ideal, but it's not maximal. Okay, so you have a maximal ideal 0 in Q, but when you pull it back to Z, you still get the 0 ideal in Z now, but it's not maximal. So in general, inverse image of a maximal ideal is not maximal. So this completes the problem, but let me give you an exercise. Suppose phi from R to R prime is a surjective ring homomorphism. Suppose this is a surjective ring homomorphism and let I be maximal in R prime, then show that phi inverse I is maximal in R. So the idea is, the statement I just disproved in general, that inverse image of a maximal ideal is not in general a maximal ideal, in fact becomes true if you add a condition that the ring homomorphism is surjective. Okay, that's important. If that happens, it's true. Of course, the example from Z to Q is not surjective. There are lots of elements in rational numbers which are not in the image. Any rational number that's not an integer is not in the image. So why is this true? This exercise, the hint is actually just to use two facts. First, note that R prime is isomorphic to, in fact I'll write it like this, R mod kernel phi is isomorphic to R prime, right? Because it's a surjective map, and first isomorphism theorem says that R mod the kernel is isomorphic to R prime. Second, use the correspondence theorem or the slightly stronger correspondence theorem that I stated at the end of the previous video. The correspondence theorem says that ideals in R mod I are in bijective correspondence with in ideals in R containing I, but that you can put adjectives to these statements, prime ideals on both sides or maximal ideals on both sides, and the correspondence theorem still holds. Use that second, the more stronger version of correspondence theorem for maximal ideals to do that, because if you take a maximal ideal in R prime and its inverse image will be maximal because it just corresponds to an ideal in R that contains kernel phi. Okay, so this last exercise that I did today is very easy, but it's important for us. We will often use in future that inverse image of a prime ideal is prime for any ring homomorphism. This statement is not true in general for maximal ideals, but if the ring homomorphism is surjective, the statement is true. Inverse image of a maximal ideal is maximal. So far in the last few videos we have learned about primes and maximals ideals in rings, and we did a number of exercises. So hopefully you got some understanding of how to work with prime and maximal ideals in rings. So in the next video we will start talking about field of fractions of integral domains, unique factorization domains, and principal ideal domains. Thank you.